Hello everyone, and welcome to this talk. So in this talk, we will explain how we found some vulnerabilities in a leading BGP implementation and what are the security implications. So first, a quick word about who we are. So this vulnerability research work was done by Stanislav Dashevskyi, Amine, Amri, and Oussama, Kerro, and under the direction of Daniel. We all work at VDR Labs, which is a team at Force Code Technologies, and our mission includes vulnerability research, threat research, and threat intelligence. First, so we already presented previous vulnerability research. In particular, we had Project Memoria, which is an initiative in which we analyzed 13 different TCP IP stacks that we found inside OT and IoT devices. And in total, we found 61 vulnerabilities. And we were able to find patterns in these vulnerabilities. And we even published an informational RFC, so RFC 9267, which is specifically about DNS implementations. In general, we saw widespread problems in the parsing, and this is why we had the idea to look at BGP. So first, in this presentation, we are going to explain where and how BGP is used today, and then we will present our technique in finding the vulnerabilities and what we were able to find. But first, let's talk about BGP.
Thank you, Simon. So let's talk a little bit about BGP. I think that most people in this room already at least have a basic idea of what BGP is, but these days, BGP is used not just, as it's shown in the figure there, to route data packets on the internet between different networks, but it's also used in some different contexts, and that's what we want to go over a little bit here. But first, the internet in a nutshell, right? So we have edge devices and we have routers that connect these edge devices in different networks. The research that Simon mentioned before was performed before in these IT, IoT, OT types of devices, which are up at the edge of these networks and basically, run TCP/IP stacks, send and receive data packets to other devices, right? But those data packets, they go via routers that connect these different networks. And this research is about trying to understand a bit better the routing stacks that goes into these routers. So what is BGP? It provides routing for the internet, right? So it's a protocol to exchange routing and reachability information among different autonomous systems, ASs. Each AS is a block of IPs that is leased to an organization by a register for a certain time period. And BGP is used to advertise these autonomous systems numbers and to peer networks that are each part of a different AS, right? And BGP can be used internally to peer within the same autonomous systems, and that's called internal BGP, or externally, external BGP peers on the internet, different autonomous systems. And BGP makes routing decisions based on paths, network policies, and rule sets to basically find the best way to send a packet from one device, one host on the network to another one in potentially a different network on the other side of the world. And again, this is what people know about BGP very well and historically what it has been used for. But these days there are some other different use cases of BGP that leverage the same protocol, the same capabilities for more internal, more organizational, let's say, use cases. Things like internal data center routing, right? So data centers have grown massively in the past decades to the point that BGP is used internally to route packets within these data centers. It's also used these days for VPNs, layer 3 VPNs using MPLS, so across different organization sites, right? So within the same organization, across different sites to set up a VPN, this protocol is used. It's also embedded in custom appliances, right? There are appliances by companies such as Netflix, for instance, that deal with some specific type of traffic. They are put on the ISP's data centers in some cases, and they have embedded BGP implementations as well. And there are other use cases, emerging use cases like load balancing and a lot of other stuff. So we just want to reiterate that BGP is these days not just for internet service providers and internet exchanges, as people still probably think a lot about BGP. So the basics of the protocol, right? I mentioned what it's used for, but how it's actually implemented very quickly in a nutshell. It's a simple state machine where peers, they're basically in an idle waiting state. Then they set up a connection, and peers keep a live connection every X seconds to make sure that the connection is still open. And from time to time, they send messages to update the routing tables of the other peers, right? So it's somewhat simple. You can see the whole state machine there. There are 3, 4, 5, 6 states. There's a limited set of messages. As I mentioned, it's open, update the routes, send a notification if there's any error, or keep alive. And the packets are also relatively straightforward, right? You have a header that has that marker length and type, and then you have the actual content of the message, which has the header and the content below that, with some optional parameters. So what potentially could go wrong, right? It's not a very super complicated protocol if you look at it this way. But historically, and again, this is going back to what people typically talk about BGP. BGP has no built-in security per se, right? Like DNS, like many other early protocols in the internet. So there's no authentication, authorization mechanism kind of built into the original protocol. So there are mistakes or intentional attacks that lead to network outages and traffic redirection when autonomous systems or routers actually advertise IPs, blocks of IPs that they are not actually responsible for, right? And there are hijacks and leaks. And again, this is something that has been discussed for many years. When networks are originating, that's the BGP jargon, a prefix that is owned by another network without the permission of their network, and sometimes propagating that routing announcement beyond its intended scope. And it's been known for a long time, but still there are potentially thousands of incidents per year, right? And there are organizations that track these incidents. They happen frequently, less frequently than in the past, but still somewhat frequently. And there are, from time to time, big cases that lead us to wonder, if it's a potential attack or not, right? When countries like China and Russia are involved in the headlines that you see there on the slide. So traditional BGP security, with all that in mind, has typically dealt with filtering incorrect or malicious routing information, right? So you have nowadays lots of techniques and ideas that are being implemented slowly, because as everything in the internet infrastructure, this takes a lot of effort and implementation from different ISPs, people to agree and coordinate on implementations and so on. But these things are being implemented, right? Origin validation, path validation, using things like RPKI. So basically verifying that whenever a network announces a route, it is actually somewhat authorized to do so. But in all of this context, we see that there is not often too much discussion about vulnerabilities in BGP implementations, right? Rather than talking about the protocol per se and how to add new features to it. As Simon was discussing before, we see that a lot of parsing in other protocols, in TCP/IP stacks, for instance, is done, or historically has been done, in a way that has led to bugs, and we don't see too much discussion on BGP implementations about that. There are instances already where BGP has failed because of software flaws, so not BGP the protocol itself, but BGP, an implementation of BGP, so basically the use of the protocol on the internet has failed because of software flaws. There was an experiment in 2019 where some researchers were trying some new features of BGP that was not supported, and they were using the FR routing implementation, which we'll discuss a little bit more in the rest of this presentation. And that was supported by a subset of routers, not by others, and basically that took down some routers that couldn't process some messages, and it led to some crashes. Of course, in the end, the internet recovers and things go back to working, but for a limited period of time, there is an outage caused by software flaws. So, in a nutshell, why do we want to research these BGP implementations then? The latest systematized work that we found about testing BGP implementations was actually 20 years ago here at Black Hat. And I invite you to have a look at that talk. It's a very interesting talk, and it was a team at Cisco that looked at implementations and configurations of BGP across some vendors. They, like us, created a fuzzer, but that was 20 years ago, and analyzed 7 implementations and found 4 new CVs, but at that time they concluded that misconfigurations on BGP were more dangerous than implementation issues, right? So again, all the stuff about origin and path validation and so on that we discussed before. We also saw some research in 2007 from a team at Juniper that analyzed the update message handling, specifically update messages in several vendors. And again, have a look at their work. The main result of that was the finding that mishandling can lead to some denials of service. There were 7 vendors affected, 10 that declared not to be affected, and 25 that were actually unknown. They didn't answer to the disclosure. But in this meantime, there are in the NVD 129 CVs on BGP implementation, some including remote code executions, right? And 123 of those, based on our analysis, actually have to do with message parsing issues. 95% of the vulnerabilities there have to do with parsing of BGP messages. So if we drill down a little bit into these previous vulnerabilities, we see that there are a few vendors that are represented with a higher number of vulnerabilities there. It doesn't mean that those vendors are more vulnerable, of course. I mean, whenever we talk about vulnerability disclosure, that I believe that's obvious for everybody, but it just means that those vendors maybe are more transparent, or maybe are doing more research in their own protocols, or maybe because they are major vendors, people are looking at at those implementations more. But you see that Juniper, Cisco are the vendors that have the largest number of vulnerabilities there, and that's followed by FR routing, which again I mentioned before and we'll talk about later, and its predecessor Quagga. So FR routing is a fork of an open source project called Quagga. And then you have some other open source and closed source implementations as well. Most of these vulnerabilities actually lead to denials of service, 82% of them, and some others can lead to information leaks, remote code execution, authentication bypasses, and other types of impacts. And we see also, interestingly, that from 2017 onwards, there is a bit of a spike in the disclosure of these vulnerabilities. It's not entirely clear if it's because more researchers were looking at it, or more vendors, or both, but the fact is that from 2017, there seems to be a bit more interest in this type of vulnerability in BGP implementations. And if we look not just at the vulnerability research, but at the threat landscape per se, it became very, very clear this year. It's been clear for a few years, for sure, but it became very, very clear this year that threat actors have been focusing on network infrastructure very heavily, right? So we have state-sponsored actors. You have CISA alerts there that deal with state-sponsored actors looking at network infrastructure. And when I say network infrastructure, it means routers, firewalls, anything that is exposed directly and providing the basic layers for infrastructure, for networking in an organization. And it's not just state-sponsored actors, right? You also have ransomware groups, cybercriminals, hacktivists, and so on. Actually, very recently, a couple of months ago, there was a binding operational directive from CISA talking about mitigating risks of exposed management interfaces of network infrastructure specifically. And we see that there are still several BGP implementations that were not systematically analyzed. And there are open BGP implementations that are gaining they're becoming very popular, right? Gaining traction with a new or somewhat new trend called NFD, or Network Function Disaggregation. So basically, nowadays it's more popular, or it's becoming more popular, that the hardware and the software in a network appliance, such as a router, are provided by different vendors, or kind of mixed and matched, rather than the traditional model where the software, the hardware, everything was provided by a major vendor as one piece of equipment, right? So there are many different implementations of routing platforms, network operating systems, looking glass servers, and other routing components that haven't been analyzed, as I mentioned in the previous point. So we cataloged actually 52 different routing protocols. 40 of them are open, 12 are actually closed. 20 routing platforms, 17 open and 3 closed. And 53 different network operating systems. Out of those, 20 were open. So we had to really narrow down the scope of this research into what we wanted to do. And just to go a little bit further into the threat landscape, right? CISA also maintains a catalog of known exploited vulnerabilities. And if we look, most of the vulnerabilities out there are actually affecting typical software, right? Windows, Linux, Mac OS, and things like that. But 179 of those vulnerabilities can be mapped to specific types of devices, such as routers, right? And out of those, 88 actually affect routers. So 49% of the vulnerabilities that we looked at that can be mapped to specific devices are mapped to routers. And there has been some past research into why routers are so popular an attack vector. It's pretty obvious, right? Because they are internet facing and they can provide a very good initial access point into an organization. But I invite you to have a look at those presentations as well. And the last slide of this kind of contextualization part, out of those 88 vulnerabilities, we also see that 3 vulnerabilities are CVEs affecting Cisco BGP implementations they were added to the CISA catalog in 2022, so they were being actively exploited into 2022. And some of them are actually kind of decades old, right, from 2010, 2009. So it's not like just the latest and greatest popular vulnerabilities that are being exploited, but things that are more than 10 years old, still affecting routers out there and still being exploited by threat actors. We also saw 2 other denial of service on Cisco implementations, but they are affecting a different protocol called DVMRP. And that was it for this part, so let's see how we actually found some new stuff.
Yes, so now we'll talk first about the methodology of what we did to find these vulnerabilities. So for this analysis, we first looked at the implementations where previous researchers found the vulnerabilities. And then we looked at the most popular BGP implementations. And so this led us to select multiple implementations, both open source and closed source. And for the actual analysis, we used our previous knowledge of vulnerability research on network protocols. And we also looked at RFC non-compliance. And of course, for closed source implementations, it was more difficult to look for the vulnerability patterns that we knew. So we decided to use the fuzzer in the end. And actually, we ended up using the fuzzer also for open source implementations. So there are some specific anti-patterns that we found during this research. Some of them are directly protocol issues. So first we have the BGP messages that use type length value fields, which means parsing is more prone to errors. And another common issue is the possibility of optional parameters. So again, it's something that is sometimes not handled correctly, as we will see in the vulnerabilities that we found. And an interesting thing to know is that most of the time, the BGP peers, so the peers, they answer to any open message, and because open message is actually used to establish BGP peering, so BGP connection, and sometimes they also accept update messages without prior peering. And since this is a stateful protocol, as Daniel explained, it can be difficult to do the exception handling, and the parsing also is more prone to errors. And so in the end, we focused mostly on open and update messages because, as we saw, they can sometimes be parsed before having a previous BGP connection established. So for open messages, we compared some implementations and we found a few things. First, in most cases, the BGP daemon runs in user mode, which means that there is always a complete TCP handshake before a rejection, because the TCP handshake is handled by the kernel. So an application running in user mode cannot block the connection before the TCP handshake is done. And so this is true except for Cisco iOS. And the second interesting thing is that the particular implementation called FR routing does some processing of the open message before the peer is validated, because in the open message you have specific fields that allow for the identification of the peer that is trying to connect, but FR routing does do some parsing of the open message before this check. And so now about the fuzzing we did. So first a quick word about fuzzing. So the goal is to give general direction to a program that will do the vulnerability testing for us. So it will generate random payloads that look like real BGP packets, but the specific fields inside the payloads are either randomly generated or set to problematic values. And we run this program in infinite loop, and we just wait for the target to crash. So during the making of this fuzzer, we could not find any open source BGP fuzzer. So we used the BooFuzz, which is a framework used to create fuzzers. And after making this fuzzer, we only need to have the BGP daemon running, for example, in a virtual machine, and then the fuzzer will establish a connection with BGP daemon and try payloads until the BGP daemon crashes. So here is a demo video of the fuzzer running. So on the right, you will see the BGP daemon running, and the terminal on the left will be the fuzzer running. And so now you have the BGP daemon running on the right, and now the fuzzer is going to be launched. Now it's sending malformed packets in a loop, and it will soon cause a crash in the BGP daemon. So now it crashed, and as you can see, the BGP daemon restarted automatically because the fuzzing is automated. But in this case, also on the left, you can see that the fuzzer generated a file that contains the specific payload that made the BGP daemon crash. And now we are going to launch again the BGP daemon, but this time inside the debugger, so we can find the root of the issue. Okay, so now the BGP daemon is running again in the debugger. We are going to execute the payload that made it crash the first time. And now it crashed again, so we are going to look at the backtrace to see what happened. And you cannot see it, but it's a function that was called inside the function called the BGP open receive, which is a function that contains open message parsing. So it shows that there is an issue in the parsing of open messages in this BGP daemon. So in total, we quickly found 3 issues using the fuzzer, and they were all due to wrong parsing of the BGP open messages. And what is interesting to mention is that these issues are very similar to other vulnerabilities that were previously found in the Cisco iOS. And also we wanted to mention that it was really easy for us to report these vulnerabilities, and they were fixed very quickly by the FR routing team, and because it's an open source project. And now we are going to see the vulnerabilities in detail. So the first issue was in the BGP open receive function. And actually there are two issues because there is a check on line 4 that checks if a parameter called extended optional parameter length is present in the BGP packet. And we can pass this check if the byte at this if this byte is equal to FF, and it will cause the read of the next byte of the packet, but there is never a check to see if actually the packet contains something after the length byte. So in this case, we can read 1 byte beyond the packet. And then just below, you have another check, which is exactly the same thing. But this time it's reading 2 bytes after the packet. So it's a single issue. For the next one, it's also due to the optional parameters. So this time it's the issue that we saw in the video. So it is in the PIC4IS4 capability function, which was called by the BGP open receive function. And it's again due to insufficient checks on the bounds of the packet, because on line 12 you have a check that sees if we can go 2 bytes after the length parameter, if you can read 2 more bytes, but after that there is a line that tries to read 2 more bytes, but if the line works and there is actually extended length parameter, we will read 1 byte more, which but we only checked before if we could read 2 bytes, not 3. So it's another issue where we read beyond the packet, beyond this in the packet. And so finally, for this third vulnerability, it's almost the same as the previous one, because this time it's the code accounts for 2 bytes again for regular packets, but if we have the extended option length, it will again try to read 1 byte more. So it's again a read out of bounds.
Yeah. Thanks, Simon, for the details on the techniques and the vulnerabilities. So I think summarizing what's interesting that we saw there is 2 things, right? So the handling of open messages that in some cases is a little bit insecure, right? So in other contexts, we have called that in the past shotgun parsing, right? Where you parse kind of, you check the structure of a packet and parse the messages at the same time, right? So that's what we see in some cases with open messages, where basically it's not checked that the message is actually conforming, let's say, before trying to do the actual parsing for some data, right? So that can lead to mistakes. As I said in the beginning of this presentation, we have seen that in the past with TCP/IP stacks, and we see that again now with BGP implementations. On the other hand, beyond that, it's also interesting to see that even with leading implementations and popular implementations, with a fuzzer you saw in the video 2-3 minutes running, you can actually find some issues. It doesn't mean that you will find an issue every 2-3 minutes that you run that, because after those 2-3 minutes we ran the fuzzer for some more hours, and then we didn't find, it's not hundreds of CVEs there, it was 3, but it's interesting to see that there are some low-hanging fruits still in some implementations, right? But heading on to the conclusion of this talk, right? So let's talk a little bit about what this actually means, right? Any of these 3 new CVEs leads to a denial of service on a vulnerable BGP peer running FR routing, the vulnerable version, of course. But what that means is that it drops all the BGP sessions and the routing tables and renders the peer unresponsive for some seconds. It's a daemon, so the daemon will typically restart, but you can prolong that. It's just a malformed packet in an open message, right? So you can prolong that by sending these malformed packets over and over again. again, going back to what I said, 2 of those issues actually can be triggered before FR routing validates the BGP identifier in the ASN field. So that means you don't need to be peered, you don't need to be trusted by the other peer. In these cases, you only need to spoof a valid IP address to send an open message. And beyond just these 3 vulnerabilities that we found, talking about the others in the past, right? There are close to or more than 330,000 hosts with BGP enabled on the internet, the general internet, looking at Shodan there, a scan of the IPv4 space, you see more than 330,000 hosts with BGP. More than 200 hosts actually run Quagga, the predecessor of FR routing, which not all of them are running BGP, right? They also run some other protocols. Doesn't mean that out of those 300,200 run Quagga, but it's still a very popular implementation. And more than 1,000 are running FR routing. But it's interesting to see that even the predecessor of FR routing is still super popular. So that means some vulnerabilities from the past, from those hundreds that we saw in the past 20 years, can still be leveraged by threat actors. And then we come to supply chain issues, right? Which, whenever we talk about open source and things that will go into appliances from vendors and so on, supply chain is a big topic these days, and it's a big issue, because if you look at FR routing specifically, there is a timeline there. It was initially Zebra, then it became Quagga, then it was forked into FR routing. They're all popular projects, but if you look at FR routing specifically, it has more than 1,000 forks on GitHub. So even if these issues were fixed very quickly, as Simon mentioned on FR routing, you never know when these fixes will go into downstream projects, right? And that's something we faced in the past with disclosures that never actually made it into the downstream projects. And then that specific implementation, FR routing, is used by network operating systems that are open source as well, such as Dant, Sonic, Cumulus. There are many popular ones these days. And that gets implemented into an appliance from a networking vendor, or a router from a networking vendor. And that is then used by an actual end user, right? So there are at least these 3 steps between an end user having a router on their network and the actual original project that fixes these issues, right? So of course, having these patches trickle down the supply chain is sometimes complicated, and even getting vendors to acknowledge, to understand how they're vulnerable is difficult. So let's talk a little bit about risk mitigation, right? With everything that we said in this presentation, we still want to highlight that routing security is still very important, right? I started by saying that a lot of attention has been given to routing security in the past, and not so much to vulnerabilities in parsing. But we still need to look at routing security, right? So there are many projects like Manners, different RFCs, different guides from NIST and others that deal with path validation, origin validation, and all the typical BGP routing security. And please do have a look at that and make sure that if you're implementing BGP, you do it securely. But threat actors have also been attacking network infrastructure devices directly, right? So don't forget about software vulnerabilities, patching devices, and all that. And to patch those devices, you first need to, of course, identify all the devices in your network that may be using BGP. As we said in the motivation section, it's not just, ISPs and internet exchanges, routers that are running that, right? In your organization, you have potentially BGP as well, even internally in data centers. And yeah, the fuzzer that we released comes with pre-prepared test cases for the CVEs that we found. So if you want to test, if you know that you're running a FR router and you want to test those specific CVEs, you have just Python scripts that are distributed with the tool. If you want to run that against a new implementation, you can do that by extending the fuzzer, or let us know and we can work together. So takeaways and future work, right? So takeaways, BGP is crucial for the internet and widely used beyond internet service providers and internet exchanges. Unlike embedded TCP/IP stacks that we researched in the past, the BGP implementations have actually matured very well, and in general do not have very obvious mistakes, right? We did analyze 7, so finishing with a kind of a positive note. We did analyze 7 implementations, and we only found issues in 1 of them, and it was 3 issues, as I said, not hundreds, right? But some popular implementations, such as this one, still have vulnerabilities or are too permissive with open messages and other types of messages. With network function disaggregation, this will make some open implementations become potentially very popular, so it's important to keep the security of these projects in check. And threat actors are exploiting these kinds of issues, and the mitigation should not only be about routing security, and it's not entirely up to your internet service provider, right? It's up to everyone to make sure that BGP is implemented securely. We do have a bit more information in a technical report on the link shown there on the slide. And as future work, we invite everybody to keep fuzzing new versions, new implementation, improve the fuzzer. It's an open source project. It's on GitHub. Feel free to send pull requests, contribute to it, talk to us about how we can work on it together. And we also invite other researchers to look at other parts of the routing attack surface that we mentioned, right? Like other routing protocols, looking glass servers, remote control, and other things like that. So that's what we had for today. Thank you so much, and we'll be taking questions in the rep room. Thank you.